My name is David Oxlade and I'm a GS consultant at Mott MacDonald. My presentation today is about the automation of a national noise model with FME and data innovations. The Environmental Noise Directive requires that every 5 years, DEFRA produces a noise map which shows people's exposure to environmental noise. So we have been working for DEFRA to produce a new noise modelling system, and I've connected with their domain experts as well as those from other partner organisations on aspects specifically such as data analytics and database design. And in the presentation today, I'm going to be giving an overview of the system we produced, and we'll give you some background to the product to start with, and then we'll look in more detail about how FME is being used specifically for the production of those tools. And then we'll later look at how we've created a national scale data set and how, again, FME was fundamental in helping this new production and overcoming the challenges that that entailed. So the aim of our new noise modelling system was to allow DEFRA and other public organisations to model and report noise in a more real-time and automated manner. The objective was to design and build a data-driven system that can consume data from multiple sources, pre-process it, analyze it, and create standardized sound source and propagation models from that data. So the sound source model defines the location and the level of noise at that location by combining comprehensive data on road and rail activity, and then it uses industry standard noise assessment methods to estimate the noise levels using that combined data. The propagation model provides a model of the environment in which the noise propagates and is used for noise modelling and reporting the level of noise that receivers such as buildings are exposed to. In this presentation, I'll be talking exclusively about the road sound source data engines that I helped to develop. I'll be giving examples of the data, what was read in and consumed by the models, and specifically how in FME. And also, because this is a national scale product, I'll be talking about the challenges that were presented in producing that national data set using these tools for the first time, and how FME is integral to helping us find the best solutions to those challenges. So as I mentioned, it's a data-driven system that we've designed, so obviously you'd expect there to be a lot of data. The road sound source model, the backbone of that data really is the Ordnance Survey's Highway Network Road Link, which is this top left image here, and also the image on the right as well. It does contain some useful attributes to it. It contains information that would say the importance of each individual road link. So just to be clear, the road link is the road centre line of each road in the UK. Those attributes might be route hierarchy, but might tell us if it's an A road or a B road. But in order to estimate how much sound is likely to be generated on those roads, we need a lot more information than that. We need to know about how many vehicles are travelling on it, how fast they're travelling, what the surface of the road is, where vehicles are likely to accelerate and decelerate. So really, we need to combine information from many other sources where that data does exist onto that road data set as attributes before we can even start estimating noise emissions. So that's done from these source data sets here. So for example, the Department of Transport and the National Highways data sets and WebTree data sets give us traffic flow and average speed. And other data sets, for example, give us areas where we have acceleration, de-acceleration because of obstructions, as you can see in that symbology there. So that's an overview of the sound source model. So this is now an overview of the tools, the solutions that we developed to create that model, which were done entirely in FME. So it's 14 tools. They're fully automatable, and by that we mean that there's very limited user interaction at all. The user simply has to just put in the prompt, an example of which you can see on the bottom there with the input locations, the output locations, and then run 14 of the very complex tools. And I have to do nothing to the inputs and outputs, no manual editing at all before they can be used in the remaining tools. So this is an example of the entirety of one of the most complex tools of the 14. And in the next 2 slides, I'll be giving some examples. I'll be giving an example of one of the challenges that that tool specifically deals with in just a few transformers, these ones here in the top left. And then I'll be talking about how FME helped us resolve that specific challenges to do with linking data together. So, like I said, in the next section, we'll be diving straight in to look at the FME workbenches and some details of them. So this is the challenge that workbench we saw before poses, and it's to do with locating junctions that are going to influence the acceleration and acceleration of traffic. So obviously junctions impact traffic speed, and the traffic experts and consultants on our team highlighted that roundabouts and traffic light control junctions were junctions of most importance to us. Those roundabout junctions are highlighted in the OS data set, so we could easily demarcate where acceleration and deacceleration was taking place straight away for that data set, as is shown in the top left image of those three. But we didn't have information about traffic light controls from one of the survey. That information had to be sought from somewhere else. So the OpenStreet Map Highways dataset was used because that contains traffic lights, as you can see in the bottom left. When you plot those together, at the base of those traffic light symbols is where the OpenStreetMap places those traffic lights. You can see when you place them together that they don't necessarily spatially align, but there's a systematic difference between them. So we needed basically to find a technique to be able to attribute the road links with where those traffic light controls are using that data set in a systematic way. So that's what this set of transformers is doing here. What we're basically seeing is a system of buffers and spatial filters, which I'm going to highlight as two key transformers in this bookmark, which help us link those two data sets together. So at the start, we have the black road links and the nodes at the end of those road links from the Ordnance Survey data set. And we want to know which of those black nodes should be under the control of these red OpenStreetMap traffic light signals, which you can see don't necessarily spatially align. So we first use a buffer to define the distance we're interested in, 5 meters, spatial filter to filter out those road links, which is done in these two bookmarks, and then we find the road nodes that connect to those road links. And then finally, once we've done that and highlighted which road links are in proximity of those, we can then say which road nodes of those road links are within a certain distance, of this time 30 meters. So just by using that system of transformers, we've managed to highlight where the start and end of our acceleration and acceleration parts of the road network should be because of traffic light signals. So that's one example of using source data sets and transformers to link data spatially. And now I'll give another example of how we're using source data sets for a different tool. This one is dealing with traffic flow data and average speed. And specifically, what this is looking at is using data from websites. So it's using APIs, and it uses two key transformers that have that capability in FME to acquire that information. So first of all, we use the JSON reader, and that gives us one feature with a list of all the traffic counter locations from this website, which we can then explode. We can turn that each individual feature into a point, so we locate it, we project it, and then we can spatially filter it initially alongside our road links. So that initial API call is done, like I said, with the JSON reader, and has a fixed URL, which gives that single list to the whole national data set. Once we've done that, we can use a second API-based transformer, this time the HTTP caller, and specifically its GET method. And this time it's a unique call per each feature because the URL contains the site ID of the information that we want to call for that specific site. This time it's not returned as a list, but it's returned as JSON flat response point, for each feature, which we then pass using the JSON flatner to get the attributes we're interested in, which in this case are attributes about quality, and then we can filter out those sites based on quality. So just with a few transformers, we've gleaned two sets of information, and we've managed to filter out that information down to those we're interested in, both spatially and in terms of quality. So it's a really powerful system of transformers just to get that information. So that's just giving you a very brief, quick snapshot of how we're using FME to develop the tools and combine information together. But taking a step back, as I mentioned at the beginning, we're not just developing the tools, we have to produce the national data set as a whole. And given that it's the first time given that we developed tools recently, and this is the first time we've producing that national scale data set, it presented with some challenges. First of all, but it's just a large amount of data. So as you can see here, this is one 5K tile in the Greater Manchester area, and it contains over 8,000 road links. And that's just one of 5,755 tiles in the whole of England. We're not even considering Wales in these statistics. But when we developed the tools, as I said rather recently, we did it in a localized test area geographically because it wouldn't really have been feasible to try and give it all the data from the whole of UK up during testing. It would have taken too long. It would have been a long process. So that meant that there are many complex scenarios in other parts of the UK beyond that test area that may not necessarily have been addressed in development of the tool. So we always knew that there might be situations, complicated road junctions, for example, but the tool may ultimately perhaps have issues that, and in the worst case scenario, terminate, perhaps because geometry is not compatible with the transformer, something as catastrophic as that. But yet, nevertheless, we needed our 14 tools to run. We needed to run in order. We need the output of the first tool for the whole of the UK to be spot on and exactly how we need it to be before we run it through the remaining 13 tools. So we can't afford to have the possibility that there are issues in the data set. So we need it to check. We need a way to understand that this works correctly. There's a lot to check. There's over 60 attributes created just by these 14 tools. So as you can appreciate, quite a lot of challenges to get from initial tool creation design to producing this national scale data set. And really FME has been integral to helping us solve those problems. And I'll highlight two solutions really, but I would say is key to that process. And the first one was the ability to use workspace runners to break up that processing. So rather than just running this these 14 tools on nationally on the whole national data set, we broke it down into geographic portions. So we broke it down into 5K tiles. So we actually had to create a new workspace per each of the 14 data entering tools, which specifically called that workspace. So using the workspace runner, and it passed the input and output directory, but importantly, it passed the name of the specific OS tile that that data in the data entering tool would relate to. So in the data entering tool, in the bottom one, for example, here, the feature reader uses a spatial filter to read in just the data that's contained within that tile. So that works specifically well for spatial indexed formats such as GDBs and shapefiles. So that's one solution. That's great. That means that if we encountered an issue with one feature, we've dramatically de-risked the national scale production because it essentially means that it's just that 2 minutes worth of processing for that one tile that's been jeopardized, rather than what could be hours, maybe tens of hours for a national scale production. We didn't have to rerun the whole thing. We just found that one tile and found what the issue was. But still, it just means that we only have information that one tile's failed. It doesn't really help us quickly get to the bottom of the answer. We needed a different, another solution to help us with that. So the second solution is to use logging system. So as well as the translation log, which is really important to us for understanding successful workbench, we wanted to create our own logging system, which told us how correctly each translation has produced data for that specific tool. So at the end of each workbench, we have a set of transformers which carries out that logging. So some parts of these transformers are generic and used in each tool. So for example, counting if the number of features before and after is the same. But some bits are bespoke and carry out tests specific to the attributes created in that tool. So for example, saying if this attribute A is created with this value, does this attribute B also have the same value? And if it is, then that feature could be considered passed, and if not, then it will have to be considered failed. That information gets written out to a detailed log, such as this one here, so that each feature, each road link within that tile would be stated as passed, and we'll also have statistics about the actual attributes specific to that tool. But we don't necessarily want to have to trawl through all of those 5,000 Excel spreadsheets per region. So we want that information summarized to another log to make it easier to query. So we created a summary log per tile this time, so that we can see if each feature has, so each tile has passed for all the features within it or failed for all the features within it, and then we can quickly get to the bottom of which specific feature within that tile has failed using our detail log. So that it didn't halt the production too much, we can quickly go in, adapt the tools, change them where necessary, know which bits of the data sets would be affected, and then continue with production. So in conclusion to all of that, I would say that FME has been integral really both to the development of our data engine tools, but also to the national scale production of the data itself. So I'd like to thank you for listening, and I'd just like to finish by showing you a little 10-second animation of the data we produced. Pink lines are the road center lines that I've helped develop the data for, and everything else was the propagation model from which the sound would be received. So once again, thank you for listening.